Good days, everyone. We are from Group 4, TCN6213 Computer Networks. So today we're going to present our campus network design project. Our goal was to design a fully functional, segmented IPv6 based campus network simulator in Cisco Packet Tracer. So first, the campus consists of 6 key areas. First, 2 computer labs, each with 24 PCs and made up of 23 student machine and 1 instructor machine. Second, a server room housing a web server, a file server, and a DNS server, each with unique DNS name. Third, an admin office with 8 PCs for staff and interns. So this zone has no internet access and can only reach internal servers. Fourth, 5 classroom, each with 1 tutor PCs that requires internet access. Fifth, a system admin office with just 2 PCs but with full access to manage all devices on the network. And finally, a wireless network for student device, which internal server but has no direct internet access. So this network segmentation design utilizes a structured IPv6 addressing schema ranging from 2026, 2610, 0999, 1/64 to 8/64 to logically isolate functional areas. Our primary academic and instructional zones, including Lab 1, Lab 2, and the classroom, are granted full access to both the internet and internal servers to facilitate learning. In contrast, the server room use static and host-specific configuration for stability, while the system admin segment maintains full management oversight across the entire infrastructure. Finally, security is tighter for the admins and Wi-Fi segments by restricting internet access while maintaining internal server connectivity or anchored by a dedicated ISP link for external backhaul.
I'm Yao Xian and I'm presenting the physics and the logical design on the physical slides. You can see our device, the lab PC, classroom PC, admin machines and various devices are connected back to a central distribution layer. We use a star topologies where all switches fans out from a core switching core. Like in lab 1 and lab 2, each have their own access switches. The classroom, admin office and server room are connected through their respective segments. This design ensures clear cable paths, easy troubleshooting, and manageable scalability. The logical design illustrated a hierarchical traffic flow centers around a core router which connect to the ISP router via frame relay and handles the WAN uplink to streamline the architecture. Each segment, including the lab router for lab 1 and lab 2, the CNO router for classroom and administrations, and the dedicated zone for wireless and system administrations. Is logical separate through direct routing rather than violence by implementing OFPF v3. The network ensures efficient path selections across these distinct subnets, keeping local traffic content within its specific branch while routing intersegment communications through the appropriate gateway.
I'm Yi Xiangjie, and I will cover the IPv6 addressing scheme and routing configuration. Our entire network is built on the base prefix 2026 2610 099:/48. We then allocated individual /64 subnet for each zone. Lab 1 uses :1:::/64. Lab 2 uses :2:///64. Classroom 3 use the same :3:///64. Admin office is :4:///64. and wireless is :5:::/64. All configured using SLAAC, so devices automatically generate their own addresses. The server and system admin zone uses :6:::/64 with static addresses for reliability. One transit link use subnet :7 through :9, and the cloud or ISP segment uses :10:::/64, both statically configured. The default gateway for all subnet is the ::1 address of their respective router interface. For dynamic routing, we use OSPF v3 in area 0 across all three routers. OSPF v3 is the IPv6 equivalent of OSPF v2, and it automatically discovers and propagates routing information for all subnets. We verify OSPF neighbor relationship between routers using the IPv6 OSPF neighbor command. The default route to the internet is advertised using the default information originate command on the core router. The one link between the core router and the ISP router uses frame relay with DLCI value 102 and 201 for the two direction. For address assignment, most zones rely on SLAAC routers send router advertisement message, and devices configure themselves automatically. Only the server and system admin zone use manually assigned static IPv6 addresses to ensure consistency. To enforce access control between zones, we implemented IPv6 SCLS applied inbounds on the core router's interface. The rules work like this: Lab 1 and 2 have full internet and internet server access and can ping all subnets. Classroom also have full web access and can reach internal servers. The system admin office can unrestricted access internet, all server and full device management capability. The administration office and wireless zone are blocked from accessing the internet. We achieve this by explicitly denying the default route ::/0 for those subnets. However, both zones can still reach internal server because permit statements for the internal server prefix are placed before the deny rules. The server room itself has no outbound internet access. It purely serves requests from other zones. That's all from me. Thank you.
I'm Tan Kang Shen. Our server room contains three internal servers. The DNS server at host address 20 resolves two domain names, www.tmnet.mypoints, to the web server, and www.ftp.com points to the file server. We verify DNS by pinging these domain names from Lab 1, and resolution was successful. The web server at 21 runs HTTP service and hosts the university website. We test browser access from labs, classrooms, the admin office, the wireless zone, and the system admin office. All zones successfully loaded the website. The file server at 22 runs FTP service. We tested it by uploading unique text file from each zone. For example, L1S1 from lab 1 and staff1.txt from the admin office, and then downloading them back. All transfers completed successfully. Additionally, a cloud server is hosted on the ISP site, connected via frame relay. It runs HTTP service and is reachable from campus through the internet path. That wraps up our server configuration. Now I will show you the network testing, including internet access from labs and classroom, blocked internet from the admin office, and wireless DNS resolution using domain names, server access from multiple zones, and FTP file transfers. So this is our FTP. And this is for the file server of staff and the student one. This is the accessibility of web server. This is the file server of lab 1, and this is the l1s1.txt. So this is the step we upload the file to FTP, and this is retrieve file from FTP, and this is the web server. This is the file server for L1S4. This is the L1S4.txt. And this is the upload and retrieve file to FTP. This is the web server. And this is for the lab 2. This is the file server, and this is the L2S1.txt. And this is the upload and retrieve file from FTP. And this is the web server. And this is for the L2S4 file server, and upload and retrieve file to FTP. And this is the web server. So for the classroom one, this is the file server of classroom. This is the classroom1.txt. This is upload and retrieve file from FTP. This is the web server. And this is for the administration office called staff1. And this is the file server, staff1.txt, upload and retrieve file from FTP. And this is the web server. And this is the wireless network. This is the file server of wireless network called tablet. This is the tablet.txt and the upload and retrieve file from FTP. And this is the web server. And this is the service and system administration office. And this is the file server sa1.txt, upload and retrieve file from FTP. And this is the web server. So this is the DNS resolution testing test to use the lab 1 L1S1. This is the ping www.tmnet.com. And this is the ping www.ftp.com. This is the www.google.com. This is the web access verification. This is for the lab 1 L1S1. This is for lab 2. This is for classroom. This is for administration office. This is for the wireless network, tablet PC. And this is for the server and administration office SA1.